Hello and welcome back to 5-Minute Chemistry. Today we are going to talk about isotopes and nuclides. So previously we discussed the subatomic particles and how the atom can be subdivided into smaller things. So let's see how this relates to elements and isotopes. So previously we discussed about the definition of elements based on their chemical properties, so they cannot be chemically decomposed into other materials. But after the subatomic particles were discovered, what was found is that actually what defines what element an atom will belong to is going to be the number of protons. So because each element atoms has this unique property of the number of protons, they decided to use this as the atomic number. So previously the atoms were ordered by their mass, the relative atomic mass, but there was no strict rule on what makes the different masses into different elements. So the number of protons was a much more natural way to order the elements. And in this way, because the number of protons is just going up one by one, it's very easy to know if you actually missed an element, then you have undiscovered elements in your periodic table. The interesting thing that they found is that the protons and neutrons have almost the same mass. Their mass is very similar. So if you just add up the number of protons and the number of neutrons together, you can kind of guesstimate the mass of an atom. So they named the number of protons and neutrons together the mass number. Another interesting thing that was discovered is that the number of neutrons might vary in the atoms of an element. So the Dalton's atomic theory postulates that in an element, all of the atoms are the same, but it turns out that it's actually not true. So in an element, all of the atoms must have the same atomic number, so the same number of protons, but their neutron number can be different. And if two atoms have the same atomic number, but have different number of neutrons, then they will have different masses, because neutron carries a lot of mass. Those atoms are going to be called isotopes, because iso means same and tope means type, so they are from the same element, but they are different mass atoms. The reason that the number of neutrons doesn't really matter in terms of what element chemically is a material is because the neutrons don't affect chemistry. So as we'll later see, chemistry is mostly related to electrostatic interactions, mostly the reorganization of the electrons around different atoms. And neutrons don't have any charge, so they don't have any electrostatic interaction. They only have mass. So I write here that they don't affect chemistry usually, because there are a few exceptions, like for hydrogen, because hydrogen is very small, very light, and if you add a neutron to it, its mass can double, or if you add two neutrons to it, the mass can triple, and this huge 100% or 200% difference in the mass will have some considerable effect on its chemistry. In other cases, the different mass of the atoms will not really affect chemical properties. Nuclide is basically when all of the atoms have the same number of protons and the same number of neutrons. So in this case, for example, we can have this iron nuclide. On the left-hand side, in the bottom index, we will write the atomic number, so the number of protons, and then we will write the mass number on the upper index here, on the top index here on the left-hand side. So from the atomic number, we know the number of protons, and from the mass number, we can calculate the number of neutrons. So that is going to be 26 protons, and because protons and electrons have the same number in the same atom, it will be the same 26 electrons and then 30 neutrons in this nuclide. So nuclide means that both the proton number and the neutron number are fixed. So let's take a look at the atomic number of elements. I just took part of the periodic table here, and we can see that if we organize the elements based on their atomic number, based on the number of protons, what we can see is that actually it was justified previously to switch tellurium with iodine, because even though now the mass of tellurium is higher than the mass of iodine, based on their chemical properties, tellurium was fitting better with selenium and sulfur and oxygen, while iodine was fitting better with bromine, chlorine, and fluorine. And the atomic numbers, the discovery of protons, actually justifies this order. So you can see that actually tellurium has a lower number of protons, a lower atomic number than iodine. Now that we know that the elements can be characterized by their number of protons in the atom instead of the atomic mass, now it's all explained properly. Okay, so let's take a few examples here. So usually when you write the symbol of nuclides, you don't write the atomic number because the symbol of the element specifies unambiguously the atomic number, so usually that is missed here. When we talk about these nuclides, we say the name of the element first and then the mass number. So it is going to be carbon 12, which is made up of 6 protons, 6 neutrons, and 6 electrons. Selenium 80 will have 34 protons because that is its atomic number. Neutron number is going to be 46 because 80 minus 34 is 46. And the number of electrons has to be the same as the number of protons, so 34. For potassium 40, we will have 19 protons, which is the atomic number of potassium. We have 21 neutrons, and you can see that 19 plus 21 adds up for its mass number, which is 40. And then the number of electrons is 19. For hydrogen, actually, the isotopes of hydrogen, they have their own symbols, and T is used for tritium, which is hydrogen with the mass number of 3. We also have deuterium, which is capital D with the mass number of 2. So if you see T, that is actually hydrogen 3, which will have 1 proton because hydrogen is the first element. Its atomic number is 1, 2 neutrons, and 1 electron. Okay, so this is it for today, and I will see you tomorrow.